Alright, today we start the disc and washer method. And what a disc is that it is an object that's created by rotating something around an X or a Y axis. So what we're going to do is we're going to create discs, so circles. And then what we're going to do is figure out the width of the disc. So we're going to be able to find the volume of this disc, okay, by finding the area of the disc, which is the area of a circle. There's pi r squared. Okay, so we're going to find the area of the circle, and then we're going to multiply it times the width of the disc, or the height. So what this really does is it creates a cylinder type object. Now it doesn't have to be a cylinder. It could be a cylinder, but it could be many other objects as well. If you look at some of the pictures in your book, those are excellent examples of discs, and there's many different shapes, as you will see. There's two types of disc methods. You have a horizontal axis of revolution. That's where you're rotating it about the x-axis, and that's when you have a dx, or a change of x. And notice what we're doing is we are saying it's pi times r squared, okay, the function squared, and then we have our change in x, so our height. This is a formula that you have to know, or you just have to understand. I think it's easier to remember what a disc is, that it's a circle. And so you take the area of a circle, pi r squared, times the height of the change in the x. The other type of disc method is rotating it about the y-axis. Notice the only thing that's really changing are your bounds, are in terms of y, and you have a dy on the end. It's still the same formula, pi, and then you have your radius squared, or your function squared in this case, how far it is extending out. So let's go ahead and set up and evaluate this integral formed by the volume, and we're going to rotate it about the x-axis. So as you can see my line here, I'm rotating it about the x-axis. It's really hard for me to tell you what this shape would really look like here as I'm talking about on the video, but hopefully in your mind you can picture this whole object being rotated around, and it might look like it would be like a bowl shape on the outside, but it'd be all filled on the inside as well. So we were creating like this type of bowl. You can kind of see it if I draw this out just a little bit, and then it's all filled in. So maybe it's like almost half of a sphere or something. Alright, so let's go ahead and set up this integral. Our bounds are, we're talking about the x-axis here, so we're going to go from 0 to 3. 0 to 3, so I have this rectangle in here because it helps me figure out that I'm talking about in terms of x, okay? So I have a change in x, so 0 to 3. And I need pi out front because I'm going to do pi, the function squared, that's your r, how far out you're going. And then you have your dx. So now it's just simply solving the integral as we've done many times this year. So if you square a square root, you end up with what's underneath the square root. Integrate each part and plug in your numbers. I'm just keeping pi out here by itself for right now. It makes it easier, and in the end I'll multiply it through. So when I plug in my 3, I get 27 minus 27 over 3 minus 0. And that would be 27 minus 9, which is 18. And then multiply it times pi gives you 18 pi. Alright, in this next problem, I'm going to be rotating it about the y-axis. So if you look, what I've done is I've placed this rectangle on the y-axis where I'm rotating it. And then what that does is by placing a rectangle about the axis that you're rotating it, you can now figure out, okay, well this is a dy problem because my base of my rectangle is, or my little section, I shouldn't necessarily call it a rectangle, but it is. My little section is on the y-axis. So this is going to be a dy problem. So when we go to set up the integral, we are going to have pi, but our integral is going to be talking about on the y-axis and the bounds on the y. So I'll have 0 to 4. And now since it is about the y-axis, you've got to make this function be y's. You can't just put 16 minus x squared squared. What we need to do is we need to change this function into an x equals equation. So in order to do that, I would square both sides. I would move the 16 to the other side. I would divide by a negative. And then I would square root. Now, this technically does not happen all the time where you end up with basically the same problem as what you started with, but that's because this is a circle. I know I haven't drawn it very well here in the picture, but this is a quarter of a circle. So we're going to have pi, and then our disk, or the region we're talking about, squared, our radius squared, and then we have our dy. So now it's just simply integrating it. Everything at this point is the same thing we've been doing for quite some time. So we end up getting 16y minus y cubed over 3. So we'll plug in 0 to 4. When I plug in 4, I get 64. Minus 64 over 3. Minus 0. This gives me 192 over 3 minus 64 over 3, which gives me the answer of 128 over 3. Moving on to the next type of problem you guys are going to be seeing is we're going to start to talk about washers. Now, washers are very similar to discs, but what's missing is the hole. A washer, think about like if you've ever looked at the metals or they talk about a washer, you're putting on a washer onto a bolt or something, it has a hole or a section missing. So what we're going to have is we're going to have two radius. We're going to have the big R and a little r. And what we're going to do is we're going to find the area of both of those circles. So I'm going to find the area of the big circle. And then what I'll do is I'll subtract off the area of the small circle. So hopefully by me talking about the area of the big circle, here's the area of the big circle, pi big R squared minus pi little r squared. So here's the area of the big circle minus the area of the little circle. And then what you have is the width of each of those discs, or I shouldn't say discs, but little washers that creates the volume. There are two methods. You have the vertical method here, or the vertical about the horizontal axis, and you have a vertical axis as well. The only thing different is the dy's, and you'd have it in terms of y. If you look here, the way to calculate the radius is by looking at which function's on top, okay, and drawing down to where you're revolving this, so about the x-axis. And so your big R is the one that's farthest away, and your small r is the function that's closest to that x-axis. In the next video, I'll go through some of those examples. Alright, in the first problems we're going to do, we're going to find the volumes of areas, and we're giving nothing, so we're going to have to draw a picture. What we know is that we're going to have a graph, and it's going to be a parabola, and it's going to cross at 0, 0. When I plug in 1, I'm going to get 2. When I plug in 2, well, I'm concerned with that because I'm supposed to just go to x equals 2. I get 8. So there's the picture of this. I have the y equals x line, which is this axis right here. And then the x equals 2 line, which is right here. Now what I'm going to be doing is I'm going to be revolving this area about the, it says y-axis, so about the y-axis. So this is going to be, because it's about the y-axis, a dy problem, and it is a washer because there's a hole that's missing. If you look, the first radius goes clear out to here. This would be your big R. And then the little r goes to right here. So what's happening is that this is being rotated around, and what it would create is an object, something like this. It's a really bad picture. And it's got the hole in the middle, and it's rotating around. So this is just a two-dimensional shape of what's going on. This actually edge would be all the way around, and it'd be like a big bowl here in the middle, a big hole missing. We can just talk about that a little bit more in class if you want to have an idea what that looks like just a little bit better. Let's go ahead and set up the integral then for this. So the volume is going to be pi from, and remember we're talking about the y-axis here, so I'm going to be going from 0 to 8 on the y-axis. And then we have to take big R, well, big R was this blue line, which is the 2, and square it, minus, and that was okay to leave it as 2 because it was an x equals equation, minus the black curve squared. The problem with that is it's not in x equals form, so I've got to rewrite this. This is y over 2 equals x squared, and so x is equal to the square root of y over 2. So I've got to plug in the square root of y over 2 squared. And this would be dy then. Now it's just simply integrating. So we're going to go from 4 minus, this would be y over 4, excuse me, it'd be y over 2. I'm not seeing the square root around the whole function. It needs to be dy. So you end up getting 4y minus y squared over 4 from 0 to 8. So you plug that in, you get 32 minus the 16, and then when you plug in 0, you get 0, so you end up with 16 pi. So this is the first problem of a washer method. Alright, this is the exact same problem that I just completed on the last video. The only difference is that now I'm revolving it around the x-axis. So what I'm going to do is I'm going to create that same picture. So there's a point 2, 8, 1, 1, and 0, 0. And we're still going from the 0 to 2 part. So we're talking about this region. The difference is now that I'm rotating it around this axis. So what it actually does is it creates not a washer this time, but a disc. Here's the little section that I can talk about drawing in. Notice how it sits on the x-axis, and I can see that it creates a disc. It'd be in the shape of something like this, and it might look like a cone that's kind of flat or with some scoop sides on it when you rotate it around. So it's an entirely different object that you get when you rotate it at about a different axis. So now what I want to do is define a volume of this disk. This happens to be a disk in this problem. So I'm going to just have one R, and R would be the 2x squared, and I have to still square it. We're talking about going from 0 to 2 because we're going about the x-axis. So when I go and I square this function, I get 4x to the 4th dx. Now when I integrate it, I get 4x to the 5th over 5 from 0 to 2. And then I'll plug in the 2 and I will get 32 times 4 all over 5 minus 0. That happens to be 128 pi over 5 is my answer. I have one more of these, and this time it's the exact same function. The difference is, again, where I'm revolving it. So, draw the picture in again. This time, I'm revolving it about the y equals 8 line. So you have to decide if this is a disk or a washer that we're creating. And notice I'm revolving it about this, so I can't create that rectangle right there. But the rectangle would be going in this, or the section would be going in this direction. This is obviously going to be a washer because I can see the hole that's created. So the little r, this would be the little r, the hole that's created, is created by the function 2x squared. And then the big R is the difference here between 8 and 0. So it ends up just being d8. Now I do need to make a correction here. My little r is a little wrong, so I need to fix this. My little r ends up being, it's going to be 8, the top function, minus the bottom function. So it's 8 minus 2x squared. So I'm going to go ahead and set this up. I don't know if I'm going to have time to solve this, so we could do that during class. But this is about dx, so it would be from 0 to 2 pi. It would be the big R squared, so 8 squared, minus the little r squared, 8 minus 2x squared squared. In order to find this integral, you'd have to square each of the parts, which would require you to FOIL here, so you'd end up with 32x squared plus 4x to the 4th. And then you have to integrate each part and plug in the numbers. I don't have time to complete this problem, but I could do that during class.